So next we're going to have a tutorial on RLlib, which is a scalable library for implementing reinforcement learning algorithms and running them at scale. The tutorial is going to be presented by Liang. He's a grad student in the RLlib. Eric, you have the mic.
Thanks. Hey, I'm Eric. I'm here to tell you about building RL applications with RLlib. So this tutorial is going to be an overview of reinforcement learning and RLlib. And the focus is really going to be on applied reinforcement learning. So we're going to understand how to model problems as RL environments. We're going to deploy. We're going to use RLlib for distributed training and simulation. And then we're going to learn how to deploy a simple policy server with RLlib. And if you want to learn more about the kind of nuts and bolts of RLlib, which we won't be covering as in-depth in this presentation, you can check out the documentation online at rlib.io. Also, you can check out the ICML18 talk. Great. Before we dive into RL, let's first understand the difference between RL and supervised learning. So in supervised learning, you typically have some large data set. Here, a data set of animal images. And then you have a bunch of labels. So here, what category the animal is. And the goal is to train your model to make predictions about the inputs. So here, we're just predicting label outputs, which is what type of animal. And then you can deploy this trained model in production, and then you can make predictions on new data. For example, you have a new novel image of a cat, and then you can predict, like, yes, it's a cat. So you can imagine how some variations on this sort of model might be very useful for applications. However, in the real world, applications are often more complex than this. So as one example, let's look at a web store applications where you have users interacting with some online store. So an interaction with this application might look like this. The users might search for some items. You get results back for your search. The users might take actions like adding items to the cart, and your service gives them suggestions to help them along. And finally, the user checks out. And this realizes revenue, and it's kind of the goal of your application. So the interesting thing with RL is that there's a very natural mapping of this sort of application into the RL formalism. So formally, RL, the users kind of comprise an environment, which is the real world, and your service is an agent that's acting in that environment. So those actions of the users are actually observations. So this might include what the user is doing, their profile, things like that. And in response, your agent is taking actions to try to improve its reward, which is in this case a very clean mapping to revenue. So really the difference between RL and supervised learning is that reinforcement learning is centered around interaction with the real world. So you have some agent with some policy, typically a neural network, and this agent takes actions, interacts with the environment, receives observations and rewards, and based on these experiences, your agent learns to take better and better actions. And reinforcement learning, specifically deep reinforcement learning, has really only started working a few years ago with the advent of deep learning. And one of the first major successes was AlphaGo. So you probably heard of this. DeepMind trained a deep reinforcement learning agent to beat humans in the game of Go. And the setup here is pretty simple. The observations are the board state. The actions are where do you place your next stone. And the reward is a very simple thing. You get +1 if you win, -1 if you lose. And yep. And since then, researchers have been applying RL to a number of other applications. So one kind of interesting application I ran into recently is for cellular antenna tilt control. So you can, in the real world, you have these cellular antennas, and then there are many of these antennas deployed over a city, and you want to maximize something like maximize user bandwidth. And you can adjust these antennas in various ways, either physically or electronically actuate them to control the tilt of individual antennas. And the problem here is how do you adjust this stuff automatically? And it turns out this can be framed as an RL problem. The observations are the positions of the users and the user signal strengths. The actions are, of course, what antennas you adjust, and the reward is overall network throughput or any other metric you care about. RL has also found applications in some other more classic optimization problems. For example, database query optimization. And so one classic problem in query optimization is how do you optimize a query plan? So you can look at this as follows. So the observations are the relations you joined so far, and the remaining relations, the actions are which relations to join, and the rewards are the cost of the query. And yeah, so what's the difference between, so we saw a lot of differences. Something in common between RL and supervised learning is that they both require lots of training data. So in supervised learning, you have large labeled data sets. It's kind of a requirement for training these deep learning models. In RL, we're fortunate that you can actually generate data through simulations. So you can generate virtually unlimited data if you have an accurate simulation. Or alternatively, if you can deploy your system at large enough scale and collect lots of data or through logs, yeah, that will also suffice. So we see large companies starting to experiment with RL for applications such as search ranking, feed ranking, things like that. And yeah, so another thing in common is both RL and supervised learning require scalable software libraries for our training. And this is where RLlib comes in. So RLlib is a framework for scalable applied reinforcement learning. It's one of the growing number of libraries built on top of Ray. And zooming in a little bit, RLlib builds on Ray's tasks and actors, which you've seen in a previous tutorial, to provide abstractions for RL. So this enables RLlib to implement a broad range of algorithms at scale. And then, most importantly, RLlib provides application support. So for simulation, training and simulation, for policy serving, learning on data, and so on. RLlib's a unified framework for scalable RL. So thanks to its abstractions, it's able to implement a large number of state-of-the-art algorithms. And these algorithms were originally implemented as specialized systems, but in RLlib, we're able to implement these algorithms and achieve state-of-the-art results all in one system. Yeah, RLlib has a large and growing number of algorithms. And many of these algorithms are community contributions from, for example, Berkeley Flow Lab and people from Alibaba. RLlib importantly has general purpose APIs, so each of those algorithms can be leveraged in many different ways. So for training and simulation, as you'll see in the tutorial, policy serving, and also if your problem can be better set up as a multi-agent problem, it has APIs for this as well. So how do we actually apply RL to solve problems? So let's remind yourself what the goal of RL is. And typically, you have this function PyTheta, which is the policy of your agent, and that policy takes in an observation. So in this example, it's some image, and then your agent's going to, based on that observation, make some action. So here, I guess turn based on the image, turn left or turn right. And the goal of RL is to learn this function through experience. So what is the problem setup? First, you have to define your environment. So this is the action space. What sort of actions your agent's going to take? Is it just does it have just a choice of a couple actions, or is it something more complicated? Like it might be you have a vector of floats or some other composite structure for your actions. You have to define what your space of observations is. So this might just be a simple image. It might be a vector or some combination of this. And finally, you actually have to implement your environment. So this involves interfacing with the simulator or perhaps a system. You need to pick RL algorithm. There's a lot of freedom here, but typically you choose this from some library like RLlib. And then you choose a good network model for your policy that ideally models your environment well. Cool. Yeah, so the next step is you collect experiences, and this is done by running your policy in a loop. So your agent takes actions, gets returns, and this loop is repeated until you have enough experiences to learn on, and then you improve your policy. So then at a very high level, this can be implemented as a gradient ascent over the estimated reward surface. So you're basically just trying to get your policy network to improve the probability of taking actions that lead to good rewards, and this is super high level. And in RLlib, step 2 and 3 are basically managed for you in a distributed way, so you don't need to worry about too much. But to learn more, you can check out our documentation, and Berkeley and other universities also have great resources on learning more about deep RL. Cool. So The goal of the tutorial today is to use RLlib to build a simple web application, Pong, that learns as you interact with it. So you're going to open your browser, you play Pong, and actually RLlib is going to learn to play better as you play with it. So to break it down a little bit, the first exercise is going to be learning about Markov decision processes, which is the formalism underlying RL environments. The next exercise is training and simulation with a PPO, which is a state-of-the-art policy grading algorithm. And finally, we're going to try this end-to-end Pong application.